All right, let's do part two of this chemistry stuff. A little hard to grasp some of those concepts. But we talk about chemical bonds. We just went through ionic bonds where we share. No, we don't. We either get or we give an electron, but we're not sharing it. And then the covalent bond where we do talk about sharing electrons. And the sharing of electrons can be in a non-polar fashion, like in a carbon dioxide molecules, for example, where the sharing of the electron is equal. That's non-polar. But then we have a polar covalent molecule, which is a molecule that shares the electrons unequal. And the best example for us is water on that, where the oxygen has just a little bit of a stronger pull of the electron than the hydrogen does, and that makes that pull on the oxygen a little more negative than the ones on the hydrogen, and that we can then use to create water lattices or create those molecules, bond them together again, and that would then be an attraction bond of the charges. The charges, the poles, are attracting one another. And when that happens, we call that a hydrogen bond, because that's from hydrogen is to water, and mainly that's formed by water. And those are weak connections. But we can use those bonds in the body when we need to make larger molecules. Like within a large molecule, we have bonds that make the three-dimensional structure of that molecule. And we can call that intramolecular bonds. For example, the DNA double helix has that, or we also have hemoglobins that get created and use that hydrogen bond to make the three-dimensional shape. So 3 bonds, ionic, covalent, and hydrogen. Then we have some ways of reacting chemically. We have a decomposition reaction. That's one where we make smaller molecules from larger ones. We take a large food molecule and break it down small enough that we can absorb the independent glucose or fat molecules. This is a catabolic reaction. Catabolism is a breakdown reaction. It's destructive. It releases energy when we do that, which is helpful. Example, our digestion of food, as I mentioned. Then we have a synthesis reaction, and that's when we make large molecules from smaller ones. So we synthesize something, we create something. We use that in the regular language as well. This is an anabolic reaction or a constructive reaction, and it uses energy to make that. We use that for growth, for repair of worn out tissue, for example. And then lastly, we look at an exchange reaction, and that's a reaction where the molecules basically switch. We go from, let's say we have a glucose and an ATP, and we tack a phosphate to the glucose to keep the glucose inside the cell. That's what is used in the body for that. But we're not really creating, we have 2 substrates and we create 2 end products out of it, and we flip the molecules around. Decomposition, synthesis, and exchange. When we look at things that influence the reactions, chemical reactions, it's temperature. The higher the molecules vibrate, the faster atoms move, and the higher the rate of a reaction is. Concentration is also important. The higher the concentration of an atom, the higher the chance of an interaction. If there's hardly any atom around, it's very hard to bump into another one. Particle size is important. The smaller the particles, the faster they move, the more possibility for an interaction we have. And then lastly, we have this biological catalyst, and those are enzymes that help drive reactions forward. They're like stoves or heating plates. They speed up reactions. It's kind of like in synthetically speeding up, making the temperature warmer. But that decreases what we call an activation energy, which is a starting energy that we need to drive a reaction forward. So that's a biological catalyst. And in our body, that's always done with enzymes. Then that brings us to the biochemistry, and biochemistry stands for chemistry of life. Our life on Earth is carbon-based, and biochemistry has a lot of carbon in it, and so we have large carbon-containing molecules, and those become our organic molecules. And then we got small ones that are also in our body, like water, for example. They're mostly non-carbon containing, and we term those inorganic molecules. So the carbon is what makes them organic. Water is the largest quantity one of those inorganic molecules. We have about 2/3 of our body weight is water. So it's the most abundant substance in the body. It has a few really good qualities. One is water has a high heat capacity, which means it can absorb and release large amounts of heat before it changes its temperature much. What this does, it prevents sudden heat changes in the body. That is very useful since we want to have a fairly consistent internal body temperature so we don't feel sick or chilled and the body can function properly. Polarity is also a quality of water because it's a polar covalently bonded molecule. It is a great solvent. It's excellent to dissolve solutes in it. So it makes it a great transport medium. And water, because again it's polar, it's chemically quite reactive. And so the chemical reactions, almost all of them depend on water. And lastly, it brings to it a cushioning a property. For example, around the brain or the spinal cord we have a film of water, and that makes it sort of cushioning, balances out, it decreases the quality of gravity so the brain doesn't collapse because brain tissue is very soft. It does a little bit the same as it does to you when you jump into a pool of water and you float. Or an intervertebral disc has the quality that pillow quality, or a cartilage in a joint that makes the bone not rub on each other. That's also the quality of water. That's the cushioning quality. Then the next inorganic compound is salt. Salts are ionically bonded molecules that dissociate in water into ions. And ions are charged atoms. And what they do in the solution is they create an electrolyte solution. Our main electrolytes or salts we use is sodium, chloride, magnesium, calcium, as well as potassium. These electrolyte solutions are crucial for nerve impulse, for example. They're also a part of hemoglobin. Electrolyte is a charged water that can conduct a light electrical current. And then these acid and bases, these are a little hard to understand, but like salts, when they are put in water, they dissociate into ions. And here, though, the ions are specifically hydrogen ions or hydroxyl ions. Hydrogen ions are basically an H+. And that basically is since the hydrogen ion is very small, that's basically a proton that's left without an electron. The proton is positive. So that's an acid. An acid dissociates a lot of protons in a solution. So it's also known as a proton donor. The hydroxyl ion, that's part of the base. A lot of hydroxyl ions dissociated and the concentration is high, then we call it a base. And those are also proton acceptors in the language, because if the OH, the hydroxyl ion, gets a proton, it will combine to water. A change in concentration of either hydrogen ions or hydroxyl ions is very devastating in the body. For example, hemoglobin cannot carry oxygen when slightly acidic. Well, that's a problem. That's what needs to carry around the oxygen which we need to make energy. So if we can't do that, we're screwed. So we need to make sure we balance that pH, that acidity and the acidity of the blood very well. And we measure the acidity by measuring pH. And pH is the concentration of actually hydroxyl ions. So it's an inverse proportion of hydrogen ion concentration. So a 0 indicates a very strong acid. That's a lot of hydrogen ions. And number 14 means it's a lot of hydroxyl ions that are in the solution as a concentration, and that's a strong, strong base. 7 is the neutral number. In our body, we use buffers, which are weak acids or bases that can be used to balance the pH. Because what they do is they pick up excessive hydrogen ions or hydroxyl ions. And there's the example, is a carbonic acid goes into bicarbonate ions and the proton. Don't worry about the chemical formula. Just know of the concept. All right, I think that's good enough for the chemistry. Good job.